Hello and welcome to a new lecture in a graduate course on probability theory. The purpose of this lecture is to recall some basic concepts from measure theory. Namely, I want to recall the construction of Lebesgue measure on R, and remind you of a few important measure theoretic things. So let me just recall to you at the very beginning the definition of recall. We define a measure. So a measure. So let me just say, given a measurable space, we're using omega f to denote. We denote by omega the set we're working on, and f the sigma algebra. Mu, defined on the sigma algebra, a real valued function that may take the value infinity, is said to be a measure. If as usual mu of a mu of a is bigger than or equal to mu of the empty set, which is equal to 0. So that is to say, this is non-negativity of the measure for every element in the sigma algebra. And we also have countable additivity, where we have that if we're unioning disjoint sets, ai from I equals 1 to infinity, then this will be the sum mu of ai from I equals 1 to infinity. All right. So this is the definition of a measurable space. What's so interesting, and we'll see, most of the properties you might have seen in an undergraduate course on probability theory are just properties of measures, right? Because remember, at the end of the day, what we said, recall, if mu of the space is 1, it's a finite measurable space with measure 1, we call mu a probability measure, and we usually denote it with the letter p and not mu. So many of the properties you might have seen in an undergraduate course on probability theory are just properties of measures, because recall there's this basic theorem. There's not it's an elementary measure theory theorem. We have if mu f if omega f mu is a measurable space, then we have monotonicity, namely we have mu of a is less than or equal to mu of b for every a contained in b. Of course, we're talking about AB sets in F. And we also have countable subadditivity, in the sense that if you union elements, in countably many sets in F, in the sigma algebra F, this is going to be bounded by the sum of the measures of these. So these are just basic stuff. Usually the way you'd prove such a thing is by, for example, you need to employ the countable additivity of the measure. So what you do is you'd rewrite the sets in a fancy way, making them disjoint. For example, you may write B as A union B minus A and use the countable additivity. So I'm gonna mention these tricks real quick because these are important and they show up. They always show up in application. So in applications, so for example, you may write B here as A union B minus A, and you may use countable additivity and non-negativity to get this for free. Similarly here, if you're unioning some sets in F, you have subadditivity, and the way you can prove this is by again employing the countable additivity available to you, but you need disjointness, so you require that the sets are disjoint. So what you may do here, for example, just for the sake of illustrating the trick, you may define bi to be the ith set, and you take away the union from 1 to I minus 1 of aj. In this way, the union of the bi's would still be the same as the full union, and you may now use that that the BIs are disjoint to employ countable additivity, for example, and then again you play again with the monotonicity to get the result. So two more important things that I want to mention, which are important usually to use, these are the continuity properties. So recall the continuity from below of the of a measure is as follows. If you have A1 contained in like A1 contained in A2, for example, contained in A3, and so on, and A is equal to the union of AI from I equals 1 to infinity, then like mu of A is equal to the limit of mu of AI's as let me just use n instead, as n tends to infinity. So let me clean some space up. And again, this is not hard to see. This is just like a simple application of countable subadditivity, because like the infinite sum here can be turned into like a limit of partial sums, and this is where the limit comes from. But to employ the countable additivity to the set A, for example, what you may do is you may introduce BIs, which are, for example, AI minus AI minus 1. So you may make the sets disjoint, pairwise disjoint in this way, and you will retain the property that like if you union all of these BIs, you also get A, right? And from there you can just use countable additivity, and the fact that you can write the infinite sum as a limit of partial sums, and you get the result for free. All right, so one more thing before we start talking about the Lebesgue measure. So continuity from above, a very important also property of measures. If you're having A1 contained in A2, contained in A3, and so on, so you have some decreasing collection of sets, and you know that A is the limit of them, in the sense that if you intersect them all, you get A. And in addition, you have that the measure of A1 is finite. Then necessarily mu of A is just the limit of all of these, of mu of an. Again, the reason I'm stating this theorem, though it's an elementary measure theory theorem, is to remind you that, as you'll see, like many of these, like many of the properties you might have taken for granted in an undergraduate course, are really some just like basic properties of measures, because remember, at the end of the day, the probability P that we're using is really a measure, and thus this theorem, for example, holds for it for free. And like using continuity can be quite useful, and this is why I'm stating it. I want to note something here, that this assumption is essential, and again, this is not so hard to see. The trick here is to define BIs to be A1 minus AIs, and you will see that these sets are now increasing, and so you can apply the continuity from below and get it, right? So I'll leave it to you to remind yourself of this. All right, and now let's get back to the purpose of this lecture, which is the construction of the Lebesgue measure. So remember, if we wanna construct a Borel measure on like, for example, if so let's talk a little bit about this. So if omega is R, and I wanna construct a measure on some sigma algebra, for example, if F is the Borel set, meaning it's the sigma algebra generated by all open sets in R, then like I need a function to define a measure. So the Lebesgue measure of the function f, so if you choose if you choose a function that is non-decreasing and right continuous, right? If you choose any function that is non-decreasing and right continuous, then you may define what's so-called a Lebesgue measure induced by that function, and it's the measure defined as follows. It measures this interval open at A, closed at B, by f of B minus f of A. So this is what's so-called the Lebesgue measure induced by the function f, and a particular example of this measure, particularly when you take f to be just the function f of x equals to x, then the mu of AB is just defined to be, in this case, B minus A, and this is called the Lebesgue measure. Okay, so like I really want to tell you like briefly how this measure is constructed. If you're satisfied up till here, you may like skip the rest of the video. But if you want to learn more, like if you want to know how this measure is really constructed, or you want to recall this, stick until the end of the video. So let me remind you of two very important theorems in measure theory. The construction of the Lebesgue measures is done as follows. If you have a function that is non-decreasing and it's right continuous, it's defined on R, then we can automatically get a unique Borel measure defined as such on interval AB. So this is literally the thing I stated above. I stated that if you have a non-decreasing right continuous function, you may get for free, you get a measure called the Lebesgue measure induced by f. If you want to know why this is the case, or why we can do so, or why this assertion is true, like there exists a unique Borel measure satisfying this, you may recall this theorem. So remember, the way we construct the Lebesgue measure on R is by we start by constructing like the very simple function mu on a semi-algebra, and then we extend it to an algebra, and then we extend it to a sigma algebra, and in this case we will get the claimed unique Borel measure. So let me just remind you real quick of this theorem, and this is gonna be the end of the video. So remember, a semi-algebra is just it's like just a set that is closed. So this is closed under let me just say intersection, and the complement of any set in it. If you take any set in it, like if you take any set A in it, then its complement is a union of disjoint sets. It's a finite union of disjoint sets that are in it. These are in it. So this is what a semi-algebra is, okay? So if we have a semi-algebra, this is what this theorem is, a very famous theorem in measure theory. If we have a semi-algebra S, and we have a function mu defined on S that satisfies these properties, like it satisfies these two properties, in particular, it is, namely, it is like, it's additive on a finite disjoint set. Like if you have a finite disjoint set that falls in the semi-algebra S, then it respects it in the sense that it's additive on it, and if you have if you have a countable disjoint union, then you have subadditivity. So you don't have quiet additivity, you have subadditivity. This is enough to construct a measure. This is enough to construct a measure on the on R, on the Borel set. This is enough to construct a Borel measure, and to see and this is really very powerful, because if you take just this definition, right? If you take this definition, now you note if we take S to be if you take S to be the semi-algebra of all like intervals of the form A open at A, closed at B. If you collect all of these intervals, you have this semi-algebra of these intervals. Then it's easy to verify if we define omega to be as such, then omega if we define mu to be as such, then mu will satisfy these two properties, right? And then from there we can extend this mu to the Borel measure that we claimed. In other words, we may take S bar, for example, to be the algebra generated by this semi-algebra, and the way we can do this is by taking disjoint union, finite disjoint unions of elements in S. In other words, we can take elements in S and take finite disjoint union of them, collect all of these, we get an algebra. This is an algebra generated by generated by S, and then on that algebra we may get a measure that is an extension of this function on on the semi-algebra S, and we call this measure mu2. So this is what the theorem tells us, and we may take this a further a further step, and induce a measure on the algebra, on the sigma algebra generated by the algebra S bar, right? So now we have an algebra S bar. I may consider the sigma algebra generated by this algebra, and then this theorem is telling me that I can extend the measure defined on the algebra to a measure defined on the sigma algebra, and to a unique one, in fact, if we have sigma finiteness. So I didn't intend to spend more time on this, but I just figured that recalling this theorem for you might be useful to remind you of how measures are constructed on R. So I hope this was helpful.